Assalamu alaikum students, I am Wasim Ikram. This is the 14th lecture in a series of 45 lectures on digital logic design. I hope you are well. Last lecture में हमने combinational logic पे बात शुरू की थी. हमने देखा था कैसे आप combinational circuits बना सकते हैं उसमें. आज मज़ीद उस पे बात करेंगे. But before we start with combinational logic, let us quickly revise the topics which we did in the last lecture. In the last lecture, we started our discussion by looking at the Quinn-McCluskey method. We, in fact, used the method to simplify the expression representing the odd prime number generator circuit. The number of variables in that particular circuit were, if you remember, 5. So we could not use the Karnoff map. Therefore, Quinn-McCluskey method was used. The next topic which we discussed was the implementation of combinational logic. Basically, you combine different gates to form a circuit, which is known as a combinational logic circuit. We mentioned that the combinational logic circuit is based on two forms of Boolean expressions, sum of product form and the product of sum form. So basically, the combinational logic circuit which you would implement, it would of course be based on either the sum of product form or the product of sum form. The circuit which would be required would be a combination of OR AND gates or AND OR gates. We also talked about the steps which are required to implement a circuit. So we mentioned that first of all you have to come up with the function table or the truth table of the circuit. जो भी आप सर्किट बनाना चाह रहे हैं उसका पहले फंक्शन आप होना चाहिए, डिफाइन होना चाहिए. सो फंक्शन कैसे डिफाइन करेंगे? यू नीड टू हैव ए ट्रुथ टेबल, जहाँ सारे इनपुट्स लिखेंगे, सारे आउटपुट्स लिखेंगे. उसके बाद यू कैन डायरेक्टली implement the circuit by looking at the min terms or the max terms. But the circuit, which we obtain by directly implementing it from the function table, would be quite large. It would be using too many gates. So उसके डिसएडवांटेजेस थे. हमने कहा था कि भाई पावर ज़्यादा रिक्वायर करेगा, उसका साइज बढ़ जाएगा, गेट्स बढ़ जाएंगे, कॉस्ट बढ़ जाएगी. सो द अप्रोप्रिएट स्टेप वुड बी to simplify the expressions. You have the function table, you use the Karnoff map या कोई McCluskey method use करें अगर variables ज़्यादा हैं. You come up with a simple expression. Expression किसी form में भी हो सकती है, sum of product form में हो सकती है, product of sum form में हो सकती है. उसके बाद क्या करेंगे? You can directly implement the expressions using logic gates. So you would have a simpler circuit, which of course works. हमने alternate implementations भी देखी थी. If you have a circuit, you can implement the same circuit using all NAND gates or all NOR gates. So ये circuits भी बिल्कुल काम करते हैं उसमें. Then we did an example, adjacent ones जो circuit था, उसकी हमने example की थी, उसको implement किया था sum of product form के सूरत में भी और product of sum form की सूरत में. दोनों टाइप के जो सर्किट्स थे, they work perfectly well. Now to have a look at the operation of any circuit, basically we use the timing diagrams. So हमने adjacent ones का detector circuit जो था उसके operation को देखने के लिए we drew some timing diagrams जिसमें हम input supply कर रहे थे, output देख रहे थे. So you can of course use timing diagram to view the operation of any logic circuit. Then we talked about active high or active low outputs, active high and active low inputs. Conventionally, up till now, we have been saying that the output of a circuit, any logic circuit, is 0. Whenever the output is active, the output is set to 1. Similarly, the inputs, the active inputs are treated as 1s, inactive inputs are treated as 0s. Well, this is not the case. You could have a logic circuit which could have an active output determined by a logic 0 value or logic low. So it could have active low output. Similarly, it could have an active low input. The last topic which we discussed in the last lecture was implementing a circuit for an odd parity generator. So odd parity generator से discussion दोबारा से start करते हैं. Just to remind you what an odd parity generator is, basically when you send or transmit data from one end to the other end, there are chances that some bits get corrupted. So you use a parity bit to determine an error or detect an error. So ये जो example हम करेंगे, इसमें हम use करेंगे 4-bit data. So 4-bit डाटा में अगर कोई एरर आ जाए कैसे डिटरमिन करेंगे? वी वुड अपेंड ए पैरिटी बिट, हम ऑड पैरिटी बिट अपेंड करेंगे. सो हाउ वुड यू अपेंड द पैरिटी बिट? बेसिकली वो 1 होना चाहिए वैल्यू या 0 होनी चाहिए. बेसिकली यू वुड हैव टू डिजाइन अ सर्किट which looks at the 4 bits of the data value, and then of course it determines if the parity should be 1 or 0. Once you determine the parity bit, you just combine it or connect it or append it to the 4-bit data and send the 5-bit information to the other end. So पिछली दफ़ा हमने बात की थी कि जो ऑड पैरिटी जनरेटर सर्किट है उसके लिए पहले फंक्शन डायग्राम बनाएंगे, उसके बाद फिर एक्सप्रेशंस लिखेंगे और फिर अल्टीमेटली सर्किट को इम्प्लीमेंट करेंगे. So let us have a look at the different steps. The function table represents the 16 possible combinations of 4 data bits. The 4 data bits are represented by variables D3, D2, D1 and D0. The output P represents the state of the parity bit. Since odd parity is being used, therefore the 4-bit data and the parity bit should add up to give odd numbers of ones. The function table shows the parity bit set to 1 when the 16 4-bit data input combinations have no ones or an even number of ones. The information in the function table is mapped directly to a 4-variable Karnaugh map to simplify the Boolean expression represented by the odd parity generator function. None of the ones mapped in the Karnaugh map are adjacent to each other, thus the function mapped to the Karnaugh map cannot be simplified. However, using the rules of Boolean algebra, applying De Morgan's theorem, and knowing the function table of exclusive OR and exclusive NOR gates, the Boolean expression can be simplified. Let's have a look at the simplification of the Boolean expression representing the odd parity function. The expression for the sake of simplification is represented in terms of variables A, B, C and D instead of D3, D2, D1 and D0 respectively. The expression can be rewritten in terms of common product terms A bar, B bar, A bar B, AB and AB bar, and some product terms and sum of product terms C bar D bar plus CD and C bar D plus CD bar. The expression can be further represented in terms of sum of product terms as C bar D bar plus CD, A bar B bar plus AB, C bar D plus CD bar and A bar B plus AB bar. The 4 sum of product terms represent C exclusive NOR D, A exclusive NOR B, C exclusive OR D and A exclusive OR B. The expression, if seen in terms of X and Y, simplifies to A exclusive OR B exclusive NORD with C exclusive OR D. Thus, the original 8 min-term expression is implemented using 2 exclusive OR and a single exclusive NOR gate, as shown in the diagram. Now let us have a look at the timing diagram of the odd parity generator circuit, and let's see if it verifies the operation of the odd parity generator circuit. The A, B, C and D timing diagrams represent the changing 4-bit data values. During time interval T0, the 4-bit data value is 0000. During time interval T1, the data value changes to 0001. Similarly, during time intervals T2, T3, T4 up to T8, the data values change to 0010, 0011, 0100 and 1000 respectively. During interval T0, the output of the 2 exclusive OR gates is 00. Therefore, the output of the exclusive NOR gate is 1. At interval T1, the outputs of the 2 exclusive OR gates is 1, 0. Therefore, the output of the exclusive NOR gate is 0. The output P can similarly be traced for intervals T2 to T8. If you compare the timing diagram P for intervals T0 to T8 with the values of P in the function table, you would find that they are similar, they are in fact identical. So this verifies that the odd parity generator circuit is working. We have looked at the operation of the odd parity generator circuit. In fact, we verified its operation by using the timing diagram. To implement the odd parity generator circuit, we have used exclusive OR gates and exclusive NOR gates. Basically, if you do not use these exclusive OR and exclusive NOR gates, then you can still implement the circuit using a combination of AND gates, OR gates, and inverters. But exclusive OR gates and exclusive NOR gates reduce the size of the circuit, they simplify the circuit. So what in fact are the exclusive OR gates and exclusive NOR gates? Basically, they are functional gates. These gates perform a function. What is the function? Let us discuss that. Exclusive OR gate basically detects dissimilar inputs. So let's suppose you have a 2-input exclusive OR gate. You have the combination 0, 0, 0, 1, 1, 0, and 1, 1. Now, for the combinations 0, 1, and 1, 0, the outputs are 1 and 1. For the combinations 0, 0, and 1, 1, the outputs are 0. So basically, जब भी input, दोनों input different होंगे, the output is 1. Exclusive NOR gate को अगर देखें, वो भी 4 input combinations हैं. Exclusive NOR के केस में जब combination input combination 0, 0 और 1, 1 है, the output is 1. So basically, exclusive NOR detects similar inputs. Now, how would you implement this function? Basically, exclusive OR को देखें और exclusive NOR को देखें, ये एक simple function perform कर रहा है, detecting similar inputs और dissimilar inputs. So इनको अगर आप circuit या combination circuit बनाएं, तो उसमें you would require a combination of OR gate, AND gates, and inverters. Now, since this particular function is very commonly used in logic design, different circuits use these type of functions. So instead of you having to implement exclusive OR function and exclusive NOR function by combining these different gates, you can use an exclusive OR gate, in fact, or exclusive OR gate available in the form of IC chips. Now, exclusive OR gate and exclusive NOR gate are examples of simple functional devices. When you are working with digital logic design, when you are implementing different circuits, you would be implementing different circuits which are used routinely. For example, adder circuit है, वो बहुत सारे combination circuits में use होता है. Comparator circuit की हमने बात की, again different logic circuits use the comparator circuit. इसी तरह odd parity generator circuit, again different combination circuits would be using the odd parity generator circuit. Now, if you are going to be designing such circuits, then you don't need to design the odd parity generator circuit or the adder circuit or the comparator circuit. In fact, you can find integrated circuits which implement these functions. So such combination circuits are known as combinational devices or functional devices. Now, as I said, the most common functional device which is used is the adder. So let us start our discussion with the adder circuit. Let us start our discussion with adders. Now, in digital logic, you can implement adders, of course, which add two different numbers. Now, let me pose a question. If you have to add two numbers and both numbers are of 1 bit each, how many input bits would you require for the adder and how many output bits would you require for the adder? Basically, you are adding two single bit numbers, so the input to the adder circuit should be 2 bits to represent the two numbers. Outputs कितने होने चाहिए? एक सम आउटपुट होना चाहिए, क्योंकि 2 बिट्स को आप ऐड करेंगे तो एक सम आउटपुट बिट आएगा. एक कैरी आउट भी होना चाहिए, बिकॉज इफ यू जस्ट रिमेंबर व्हेन यू ऐड 1 and 1, the answer is the sum is 0 and a carry is generated. So for a single bit adder, you would require a sum output and a carry output. Now, when you connect different adders together, then of course they add the two numbers as well as the carry borrowed from the previous number, previous two numbers. So your adder circuit should have a third input. So it should have the 2 bits to represent the 2 numbers as well as the carry in. It should have 2 outputs, the carry out and the sum out. Now, in combinational logic terminology, there are 2 types of adders, a half adder and a full adder. The half adder does not have the carry in input, whereas the full adder has the carry in input. So basically दोनों अगर हाफ एडर को और फुल एडर को देखा जाए, हाफ एडर की 2 इनपुट्स हैं और 2 आउटपुट्स हैं, फुल एडर की 3 इनपुट्स हैं और 2 आउटपुट्स हैं. Let us have a look at the functional diagram of a half adder and a full adder, and let's see how we represent the 2 adders symbolically. The diagrams represent a full adder and a half adder. A single bit binary adder circuit basically adds 2 bits and a carry bit, generated by the addition of least significant bits. The output of the single bit adder circuit generates a sum bit and a carry bit. An adder circuit that only has 2-bit input representing the 2 single bit numbers A and B and does not have the carry bit input from the least significant digits is regarded as a half adder. An adder circuit that has 3 inputs, 2 bits representing the 2 single bit numbers A and B, and the third bit representing the carry in bit is regarded as a full adder. We have looked at the block diagrams representing the half adder and the full adder. Let us start our discussion with the half adder. How would we implement a half adder? Let's first have a look at the function diagram of a half adder. Now, as we have seen, the half adder has 2 inputs, A and B. So 2 इनपुट्स के साथ फंक्शन डायग्राम में, फंक्शन टेबल में कितने कॉलम्स होंगे? 2 कॉलम्स होंगे रिप्रेजेंटिंग द 2 नंबर्स, 2 सिंगल बिट नंबर्स A एंड B. हाउ मेनी इनपुट कॉम्बिनेशंस? बेसिकली 4 कॉम्बिनेशंस, 0 0 0 1 1 0 एंड 1 1. आउटपुट्स कितने होंगे इस फंक्शन टेबल में? बेसिकली 2 होंगे. एक जो कॉलम है इट वुड रिप्रेजेंट द सम आउटपुट एंड द अदर कॉलम वुड रिप्रेजेंट द कैरी आउटपुट. नाउ लेट अस फर्स्ट हैव अ लुक एट द सम आउटपुट कॉलम. Now, sum column में कब 1 होगा? Basically, when the input is 0 0, the output is, the sum is 0. When the input is 0 1, the sum output is 1. When the input is 1 0, the sum output is 1. And when the inputs are 1 and 1, the sum is 0. Right? So basically, if you look at the sum column, the function represented by the sum column is equivalent to the exclusive OR gate function. So exclusive OR gate का अगर फंक्शन आप देखें वो भी यही काम कर रहा है जो sum output आपको दे रहा है. So the sum output can be easily implemented using an exclusive OR gate. The 2 inputs A and B would of course be connected to the input of the exclusive OR gate. Let us have a look at the carry out of the function, the carry out column of the function table. Basically, carry out कब जनरेट हो रहा है? When both the inputs are ones. For all other input combinations, the carry output is 0. So what is the Boolean expression representing the carry out function? Basically, it should be AB or product of AB. So AB जो है कैसे implement करेंगे? Using an AND gate, a 2 input AND gate. उनके दोनों inputs पे क्या होंगे? The variable A, the number A, and variable B, the number B. Let us have a look at the function table of a half adder, the expressions, the sum expression and the carry out expression, and the circuit representing the sum output and the carry out output. The half adder function table has 4 columns, 2 columns for the input and 2 columns for the output. The 2 input columns represent the 2 numbers A and B. The 2 output columns represent the 2 outputs, sum and carry out. The 2 input columns have 4 combinations of inputs, 0 0 0 1 1 0 and 1 1. The sum output shows the sum output of the half adder circuit. So the sum outputs are 0 1 1 0 respectively. Similarly, the carry out column shows the carry out output of the half adder circuit. The outputs are 0 0 0 1 respectively for the 4 input combinations. Let us have a look at the Boolean expression representing the sum output. It can be directly derived from the function table. The expression is a bar b plus a b bar. Now this expression is equivalent to a exclusive OR b. Let us have a look at the expression representing the carry out output of the half adder. From the function table, the carry out output of the half adder is represented by the expression AB. Let us have a look at the circuit. As we have mentioned before, the sum is represented by exclusive OR gate. The carry out output is represented by an AND gate. So both the exclusive OR gate and the AND gate inputs are connected together, and they are connected to the two numbers A and B. We have looked at the half adder circuit. We have looked at the function table, the expressions representing the sum output and the carry output. We have also looked at the implementation of the sum output and the carry out output. The implementation is pretty straightforward. Only two gates are used. Now let us look at the full adder circuit. Full adder circuit, as we mentioned before, has three inputs: the two numbers A and B and the carry in input. The outputs are the same as the half adder, that is the sum output and the carry out output. Again, how do we implement the full adder? Let us have a look at the function table of a full adder. कितने input columns होंगे, कितने output columns होंगे? Basically, the full adder has three input pins: the two numbers, as I have mentioned before, and the carry in. Therefore, three columns representing the variables A, B, and C, N. So there are 8 possible input combinations. Now let us have a look at the 8 input combinations, and let's determine the sum output and the carry out output. Now for a combination 0, 0, 0, the sum output has to be a 0. For the input combination 0, 0, 1, the sum output is 1. For the input combination 0, 1, 0, the sum output is again a 1. The input combination 0, 1, 1, the sum output is 0, the carry output is 1. The input combination 1, 0, 0, the sum output is 1, carry output is 0. Similarly, for the input combination 1, 0, 1, the sum output is 0, the carry out output is 1. And lastly, the input combination 1, 1, 1. What is the sum output? It has to be a 1. And what is the carry output? It is again a 1. So now we have two outputs for the sum output and the carry out output. Now, how do we implement the circuit? Basically, if you write out all the minterms representing the sum output, you can implement a circuit. Similarly, if you write out all the minterms representing the C out output pin, you can again implement the circuit. But the circuit implemented using these minterms would be using more gates. So let us simplify these expressions before implementing the circuit. So let us have a look at the function diagram, the expressions representing the sum output and the carry output, and the implementation of a full adder circuit. The function table for a full adder has 3 input columns and 2 output columns. The input columns have the variable A, B, and carry in. A and B, of course, represent the 2 input numbers, and carry in represents the carry from the previous 2 numbers. The output has 2 columns. The sum represents the sum of 2 numbers and the carry. The carry out represents the carry generated when the 2 numbers along with the carry are added together. Now let us determine the Boolean expression for the sum output. Now if you look at the function table, the sum column has 4 minterms represented by A bar, B bar, C, plus A bar, B, C bar, plus A, B bar, C bar, plus A, B, C. Now this expression can be simplified or rewritten in the form A bar into B bar C plus B C bar, plus A into B bar C bar plus B C. Now B bar C plus B C bar represents the exclusive OR function between variables B and C. Similarly, the expression B bar C bar plus B C represents an exclusive NOR function between the variables B and C. So the equation or the expression can be rewritten in the form A bar into exclusive OR between B and C plus A into exclusive NOR between B and C. Exclusive NOR is represented by the plus sign within a circle and a bar over the entire expression. Finally, the expression can be simplified to A exclusive OR B exclusive OR C. The carry out expression is represented by 4 minterms as can be seen in the function table. The 4 minterms are A bar B C plus A B bar C plus A B C bar plus A B C. The expression can be rewritten in the form C into A bar B plus A B bar plus A B into C bar plus C. C bar plus C simplifies to 1 applying the Boolean rules. The expression A bar B plus A B bar is represented by an exclusive OR function between variables A and B. Therefore, the expression simplifies to C into A exclusive OR B plus AB. Now let us look at the full adder circuit implementation. The sum term is represented by the expression A exclusive OR B exclusive OR C. So basically 2 exclusive OR gates are required. So the first exclusive OR gate is connected to the inputs A and B. The output of this first exclusive OR gate is connected to the input of the second exclusive OR gate. The second input of the second exclusive OR gate is connected to the carry N. The output is of course the sum of 3 inputs. The carry out expression is implemented using 4 gates, an exclusive OR gate, 2 AND gates and an OR gate. The term A exclusive OR B is represented by the first exclusive OR gate. The AND gate on the top does an AND operation between the output of the first exclusive OR gate and the carry N. Similarly, the second AND gate does an AND operation between the 2 inputs A and B. The OR gate basically adds the 2 product terms to give the C out output. We have looked at the full adder. We have looked at the function diagram describing the operation or the behavior of a full adder. We have looked at the 2 expressions, the sum expression and the carry out expression for the full adder, and of course we have looked at the implementation of a full adder. Now, can we implement a full adder using 2 half adders? Well, we can. Now, a half adder has 2 inputs, so at any instant it can only add 2 numbers. It would generate an output. So if you connect another half adder at the output of the first half adder and you provide, or rather you connect carry in to the second input of the second half adder, what would be the sum output of the second half adder? Basically it would sum the input A, the input B and the carry. Similarly, how can you obtain the carry out? Basically the carry out of the first half adder is ORed with the carry out of the second half adder. The output of the OR gate would give you the carry out. Let us have a look at a diagram which shows the representation of a full adder using 2 half adders. 2 half adders can be connected together to form a full adder. The first half adder is connected to the numbers A and B. The output of the first half adder generates the sum of 2 numbers A plus B. The carry out output generates the carry out by adding the 2 numbers A and B. The second half adder is connected to the first half adder. In fact, the sum output of the first half adder is connected to the input A of the second half adder. The carry in is connected to the second input, that is input B of the second half adder. What is the output of the second half adder? Basically it is going to be the sum of variables A, B and the carry in. Let us have a look at the carry out of the second half adder. It is ORed with the carry out of the first half adder. Now, what are the 2 terms? Carry out of the first half adder results in the term AB, and the carry out of the second half adder results in the term A exclusive OR B ANDed with CN. Now if you add the two terms, you obtain AB plus CN ANDed with A exclusive OR B, which represents the C out Boolean expression. We have seen the circuit diagram which shows the implementation of a full adder using two half adders. Now, a single bit full adder can only add two single bit numbers. I mean, it cannot perform some useful calculations. In order to perform some useful calculations, you need to have, let's say, a 4-bit full adder or an 8-bit full adder or a 16-bit full adder. So that means you can add two 4-bit numbers, two 8-bit numbers, or two 16-bit numbers. Now, how would you implement, let's say, a 4-bit full adder? Basically, if you have a single bit full adder and you combine 4 such full adders together, you would have a 4-bit parallel adder. We are just going to see the diagram representing a 4-bit full adder. Basically, the C out, the carry out of the least significant full adder. Least significant full adder would be adding the least significant 2 bits of the 4-bit number. So A0, B0 represent the two least significant bits of numbers A and B. So the least significant full adder would be adding bits A0 and B0. It would generate a sum output of S0 and a carry out of C1. Now, if this carry out is connected to the carry in of the next full adder, which adds bits A1 and B1, the output of the second full adder would be S1 and the carry out would be C2. Similarly, the carry out of the second full adder is connected to the carry in of the third full adder, and similarly the carry out of the third full adder is connected to the carry in of the fourth full adder. So in this manner, you can, by connecting 4 different full adders together, implement a 4-bit parallel adder circuit. Let us have a look at the 4-bit parallel adder circuit. The least significant full adder, which adds bits A0 and B0, is shown on the right. The sum output is, of course, S0. The carry in to this full adder is connected to 0 because there is no carry in to this particular full adder. The carry out from this full adder is connected to the carry in of the next full adder, which adds bits A1 and B1. The sum output is S1. The carry out, which is C2, is connected to the third full adder. So the third full adder basically adds bits A2, B2, C2. The output is S2 and it generates a carry out C3. The fourth full adder adds bits A3, B3, C3, and it results in a sum output of S3 and a carry out which is also equal to C4. We've seen the connection of 4 full adders to form a 4-bit parallel adder. You can similarly add or connect 8 different full adders to form an 8-bit full adder. You can connect 32 different full adders to form a 32-bit parallel adder. Now, we have a problem with this particular circuit. If you look at the carry output generated from one adder, it is connected to the carry in of the next adder. Now, let's suppose you have a 4-bit full adder, which we just saw. The carry out generated from the most significant full adder, that is C4, it would have to propagate all the way from the first full adder through the second full adder, through the third full adder, and ultimately through the fourth full adder. Now, let us suppose that the propagation delay for each full adder is 50 nanoseconds. So how long would it take for C4 to be valid? Basically, there are 4 full adders. So the first full adder would delay the carry by 50 nanoseconds. The second full adder would again delay the carry out by another 50 nanoseconds. The third full adder would again delay the carry by another 50 nanoseconds. And finally, the fourth full adder would delay the carry out by another 50 nanoseconds. So if you have a 4-bit parallel adder, the carry out C4 would be delayed by 200 nanoseconds. Now let us assume that you have a 32-bit parallel adder. So the propagation delay would be too long. You cannot basically wait for the carry to be generated after such a long time. Digital circuits are quite fast. So you have to find a solution to the delay. Now this delay happens because the carry has to propagate through all the gates. So what is the solution? Let us have a look at the solution. But before we look at the solution, let us just revisit that 4-bit full adder, and let's see the propagation of the carry from the first full adder to the last full adder. Consider the 4-bit parallel adder. The two 4-bit numbers A and B are applied simultaneously to the 8 inputs of the 4-bit parallel adder. Now, after a delay of 50 nanoseconds, C1 would be available. After another delay of 50 nanoseconds, C2 would be available. Again, after another delay of 50 nanoseconds, C3 would be available. And after another 50 nanoseconds, C4 would be available. Although the two numbers A and B are available, they have been applied to the inputs of the 4-bit parallel adder, but the carry, since it propagates from the first adder to the second, to the third, and ultimately to the fourth, the carry out is not available until after delay of 200 nanoseconds. So you have to devise a circuit which looks at the inputs of the 4-bit parallel adders and generates a carry. So the carry does not need to propagate through the full adder. The propagation of the carry through the 4-bit parallel adder is known as carry ripple. We have looked at the propagation of the carry bit through the 4 full adders. Now, if we have a 16-bit full adder, the propagation delay would be even more. And similarly, with 32-bit full adder, the propagation delay would increase even further. Now, we cannot afford to have such long propagation delays due to that carry bit. What is the solution to this? Basically, we need to have a circuit which looks at the inputs and predicts the value of the carry, which can be used by the full adder circuit. Now, the look at carry generator circuit needs to be implemented. So, on what basis it's going to be implemented? How does it look at the two inputs or multiple inputs and generates a carry? Let us have a look at the look ahead carry generator circuit. Consider the full adder circuit shown. The term P represents the carry propagate. The term G represents the carry generate. The carry output is going to be 1 if the term G is equal to 1 regardless of Cn. Looking at the circuit, the sum expression can be represented in terms of P and C. So the sum expression is P exclusive or C, where C is the Cn or the carry n. The carry out can be represented in terms of C, P and G, where C is Cn. So the carry out is represented by the product term Cn into carry propagate plus the carry generate. Now let us develop expressions for carry 1 output, carry 2 output, carry 3 output and carry 4 output. Carry 1 output is based on the carry input to the first full adder, the carry propagate term and the carry generate term. So C1 is equal to the product between C0 and P0 plus G0. Similarly, carry 2 is represented by the expression C1 ANDed with P1 plus G1. C1 can be represented by the expression C0 P0 plus G0. So the expression for carry 2 simplifies to G1 plus P1 G0 plus P0 P1 C0. Similarly, the expression for carry 3 C3 is represented by the terms C2 P2 plus G2. Carry 2 has the expression G1 P1 G0 plus P0 P1 C0. So the expression for C3 becomes G2 plus P2 G1 plus P1 P2 G0 plus P0 P1 P2 C0. Similarly, the expression for carry 4 is G3 plus P3 G2 plus P2 P3 G1 plus P1 P2 P3 G0 plus P0 P1 P2 P3 and C0. In all cases, the carry propagate term is represented by the exclusive OR operation between the term A and B, the two numbers, and the carry generate term is represented by the AND operation between the two numbers. So G1 would be A1 B1, and similarly P1 would be A1 exclusive OR B1. Let us have a look at the implementation of the look ahead carry generator circuit. It is shown along with the remaining part of the full adder circuit. The inputs to the look ahead carry generator circuit are the carry propagate terms P0, P1, P2 and P3, and carry generate terms G0, G1, G2 and G3. The carry propagate and carry generate terms are generated by the exclusive OR and NAND gates after one gate delay. The outputs of the look ahead carry generator circuit are C1, C2, C3 and C4. The output C1 is generated by the circuit represented by the expression C1 equals to C0 P0 plus G0, which requires an AND gate to generate the product term C0 P0 and a second level 2 input OR gate to sum the terms C0 P0 and G0. Thus, C1 is available after 2 gate delays within the look ahead carry circuit. Similarly, the output C2 is generated by the circuit represented by the expression C2 equals to G1 plus P1 G0 plus P0 P1 C0, which requires a 2 input and a 3 input AND gate to generate the product terms P1 G0 and P0 P1 G0, which requires a 2 input and 3 input AND gates to generate the product terms P1 G0 and P0 P1 C0 respectively. A second level 3 input OR gate is required to sum the 3 terms. Thus, C2 is available after 2 gate delays within the look ahead carry circuit. The output C3 is generated by the circuit represented by the expression C3 equals to G2 plus P2 G1 plus P1 P2 G0 plus P0 P1 P2 C0. The expression is implemented by a combination of 3 AND gates having 2, 3 and 4 inputs respectively, and a single 4 input OR gate. Again, 2 levels of gates are used. C3 is available after a gate delay of 2. Finally, the output C4 is generated by the circuit represented by the expression C4 equals to G3 plus P3 G2 plus P2 P3 G1 plus P1 P2 P3 G0 plus P0 P1 P2 P3 C0. To implement the expression, 2 levels of 2, 3, 4 and 5 input AND gates and a single 5 input OR gate is used. C4 is available after a gate delay of 2. Thus, for carry outputs C1, C2, C3 and C4, the delay is of the order of 2 after the propagate carry and generate carry terms become available. We have looked at the implementation of the look ahead carry generator. Basically, we implemented this look ahead carry generator for a 4-bit parallel binary adder. The expressions we derived were for C1, C2, C3 and C4. As you have seen, the expressions are based on the carry generate terms and the carry propagate terms. Now, to implement these expressions within the look ahead carry generator, you need 2 levels of gates: the AND gates, which generate the product terms, and the OR gate, which sum these product terms. So the output of the look ahead carry generator is available after a gate delay of 2. So as you can see, if you have this look ahead carry generator, the propagation delay is reduced considerably, and it is constant for all the bits. You have a 16-bit full adder circuit, then all the 16-bit full adders would generate a carry after a gate delay of 2. The 4-bit full adder are practically available in the form of integrated circuits. There are two types available, the 74LS283 and the 74LS83A. Both these integrated circuits have the same functionality, but they are pin incompatible. Now, both these chips are 16-pin integrated circuits. 4 pins are used for the input number A. The remaining 4 pins are used for the number B. You have 4 outputs to represent the 4-bit sum output. You have a carry in pin and a carry out pin. So this sums up to 14 pins. You have a pin for the power supply and you have a pin for the ground. So now you can connect these 4-bit parallel adders to form 8-bit parallel adders, 12-bit parallel adders, and 16-bit parallel adders. How would you connect them? Basically, you would connect the carry out pin of the first full adder to the carry in pin of the next full adder, and similarly the carry out pin of the next full adder to the carry in pin of the third full adder. So in this way you would be implementing a 12-bit full adder circuit. Now the carry in pin of the first full adder would be connected to ground because there is no carry to the least significant 2 bits. Let us have a look at the implementation of a 12-bit parallel binary adder using the integrated circuits which we have just discussed. 3 integrated circuits would be used. They would be connected together. So the first IC has its C in, or the carry in, connected to 0. The carry out of the first IC is connected to the carry input of the second chip. Similarly, the carry out of the second chip is connected to the carry in of the third chip. So let us have a look at the 12-bit binary adder. The 12-bit parallel adder is implemented using 3 74LS283 chips. The first 4-bit adder chip on the extreme right is used to add bits 0 to 3, the least significant 4 bits of the two 12-bit numbers. The second 4-bit adder chip in the middle is used to add bits 4 to 7, the next most significant bits of the two 12-bit numbers. Finally, the third 4-bit adder chip on the extreme left is used to add the most significant bits 8 to 11 of the 12-bit numbers. Similarly, the 4-bit adder chip on the extreme right generates least significant sum outputs 0 to 3. The second 4-bit adder chip generates sum outputs for the bits 4 to 7. The third 4-bit adder chip on the extreme left generates the sum outputs for the most significant bits 8 to 11. The carry out is generated by the leftmost 4-bit adder. It is shown as C12. Similarly, the carry in is shown connected to the rightmost 4-bit adder. It is represented by C0. Carry out of the first 4-bit adder on the extreme right is connected to the carry in of the 4-bit adder in the middle. It is represented as C4. Similarly, the carry out of the middle 4-bit adder is connected to the carry in of the 4-bit adder on the extreme left. It is represented by C8. A 16-bit adder or adders having 24 bits or 32 bits can similarly be implemented by connecting more 4-bit adders. We have looked at the implementation of a 4-bit parallel adder using the commercially available 74LS283 chips. Now in today's lecture, we basically looked at the adder functional unit. We started with the half adder, then we looked at the full adder. हमने दोनों एडर्स की फंक्शन डायग्राम्स बनाई थी, एक्सप्रेशंस डिराइव की थी और इम्प्लीमेंट किया था. Then we said that a single bit full adder cannot do any useful work. So what do? We need to combine such full adders to form a parallel adder. The parallel adder bana tha, then we said the carry has to propagate through the 4 parallel full adders. That is going to delay the carry. So what is the solution to that? Basically, we said we need to generate a carry based on the inputs applied at the full adder circuit. So we have a look ahead carry generator circuit, which generates carries which are delayed by a factor of 2. Finally, we looked at the MSI chips commercially available. Again, as we have just looked at an example, we can connect different chips together to form a 12-bit adder. We are going to stop for today. In the next lecture, we would be looking at some more functional devices. इंशाल्लाह हम नेक्स्ट लेक्चर में दोबारा मिलेंगे. अपना ख्याल रखिएगा. खुदा हाफिज़. अस्सलाम वालेकुम.